Hello student. Today we start with nonlinear applications of Opamp. The first application is Opamp as differentiator. In an Opamp as differentiator circuit, the output voltage is directly proportional to the input voltage rate of change of with respect to time. Now in this circuit diagram, the inverting terminal, it is connected to input voltage through capacitor C. Then the resistor R is act as a feedback resistor which is connected to the in between the input and output terminals. Now in this circuit, the op-amp node voltage at inverting terminal is 0. That is virtual ground concept. And then the flow of current through the capacitor, can be written as input current In is equal to If, where If is equal to minus V out upon Rf. Here we, instead of Rf, we write R. The capacitor charge equals the voltage with capacitor times across the capacitor. Capacitance times across the capacitor, that is Q is equal to C into V in. Therefore, the charge rate change is dq by dt, rate of change of charge, that is dq by dt. It is nothing but current. So dq by dt, it is equal to C into dV in by dt. But the dq by dt is the current through the capacitor. Therefore, In is equal to C into dV in by dt is equal to If. So minus V out upon Rf, it is nothing but If. So it is equating these equations. So we write V minus V out upon Rf is equal to C into dV in by dt. Now after rearranging the term, we find out the V out is equal to minus Rfc dV in by dt. Now V out is the ideal output voltage and which of the operational amplifier differentiator circuit, and it is written as V out is equal to minus Rfc dV in by dt. Thus the output voltage is a constant. Output voltage is a constant input voltage derivative minus Rfc times of the input V in voltage with respect to time. Here the sign minus sign which is present in the above equation, it specifies the phase shift of 180 degree as the input signal is given to the inverting terminal of the op-amp. Okay. Now we know the equation of output voltage for differentiator. So it is V out is equal to minus Rfc into dV in by dt. Now the differentiator circuit, it is also act as a high pass filter circuit. Now it is related with the frequency of the signal. Now let us consider that R is equal to 1 mega ohm, C is equal to 1 microfarad. Therefore RC is equal to 1 second. So V out is equal to minus dVi by dt. Now if, let us consider that Vi is equal to V sin omega t. Therefore after differentiating it, V out is equal to minus V omega RC into cos omega t. So V out is equal to minus V. Let omega is the angular frequency. So it is omega is equal to 2 pi f into RC into cos omega t. Now this equation shows that the frequency f, it increases. When frequency f of the signal increases, the output voltage also increases. That is, output voltage is directly proportional to frequency. So therefore differentiator, it is called as high pass filter. If the input of the differentiator is square wave, let us so what is the output of the differentiator? It shows small spikes in the other waveform. The means when the input signal is square wave, the output of the differentiator shows spikes. Okay. Now if The input is sine wave of the sine wave, then then this sine wave changes to cosine waveform in at the output, and which gives the signal with 90-degree phase shift. Now let us the application of differentiator. It is the main application of differentiator. It is commonly designed to operate triangular and rectangular signals. Now, generally differentiators are used as wave shaping circuits and to detect the high frequency components in the input signal. As this circuit is also called as high pass filter circuit. Okay. Now next, let us consider some important point for op-amp as differentiator. Now here, an op-amp differentiating amplifier is an inverting amplifier circuit configuration which uses reactive components, usually a capacitor, than the inductor. So the differentiator also performs mathematical differentiation operation on the input signal with respect to time. That is, the output voltage is proportional to the rate of change of input signal. Now, differentiating circuits are commonly used to operate on triangular and rectangular signals. While operating on sine wave inputs, differentiating circuits have frequency limitations. Now next, let us consider the next nonlinear application of op-amp as integrator. So for the op-amp integrator, the feedback will be provided by the capacitor among the input and output of the operational amplifier. Now this circuit can generate an output voltage which is proportional to the input voltage time integral. So thus this circuit is named as a integrator circuit. Now IN be the input current and I be the feedback current which flows through the capacitor C, and IN be the input current which flows through the resistor R to the inverting input terminal. So IN is equal to minus IF. So Vin minus Va upon R is equal to minus C d dt of Vout minus Va, where Va is nothing but V2. It is equal to 0. So therefore due to virtual ground it is 0. So Vin upon R is equal to minus C into d dt of Vout. So integrate the above equation, we can get the following equation, that is Vout is equal to minus integration of Vin upon RC dt plus C. Now the value of resistance and value of capacitor is constant, so it has some constant value. So we take these R and C like in this equation. So Vout is equal to minus 1 upon RC integration of Vin into dt. So therefore the output voltage Vout is equal to the constant minus 1 upon RC and integral of the input voltage Vin. Now this integrator, it is also called as low pass filter. So we know that in case of integrator, the output is proportional to the time integral of the input voltage. So Vout is equal to minus 1 upon RC integration of Vin into dt. So if R is equal to 1 mega ohm, C is equal to 1 microfarad, then the multiplication of R and C, it is 1 second. So Vout is equal to integration of Vin into dt. So if Vin is equal to V sin omega t, then after integrating the Vin, we get minus 1 upon RC integration V sin omega t into dt. So minus V upon omega RC in bracket minus cos omega t plus C, where C is the constant of integration. That is Vout is equal to V cos omega t upon omega RC. Now this equation indicates that as the frequency increases, the output voltage decreases. Hence, low frequency signals can pass more easily than high frequency signals in case of integrator circuit. Therefore, integrator is called as low pass filter. Now let us see the waveform. Now in this integrated circuits, they are generally used to generate ramp wave from square wave input. Here the input is square wave and the output is the ramp signal. So it is also used as a ramp generator. Now integrating amplifiers have frequency limitations while operating on sine wave signals. Now the main application of Opamp as integrator, it perform calculus operations in analog computers. So integrating circuits are most commonly used in analog to digital converters, ramp generators, and also in wave shaping applications. Now the another application would be to integrate a signal representing water flow that has passed by the flow meter. Now we have to consider some important points while studying the integrator. An operational amplifier can be used to perform calculus operations such as integration, and this configuration use reactive components, usually capacitors, and in the which is present in the feedback part of the circuit. So an integrating circuits performs the mathematical operation of integration with respect to time on the input signal. The third important point is the output of an integrator is out of phase by 180 degree with respect to the input, since the input is applied to the inverting input terminal of the op-amp. Now these are the main two nonlinear applications of op-amp. In next lecture, we see the op-amp as comparator and op-amp as Smith trigger. So thank you, students.